let's move on down to the contents and let's take a look at what I have in this define folder. So here I have my project charter. That's a Word document that I have saved as part of my project contents. And just a little background on this project. This is a real Six Sigma project that I did at Arizona State University when I was working on my Six Sigma black belt. And so as somebody who likes to bake cakes, I really can't stand ending up with a dry cake in the end after spending all that time and money. And so I actually like to use cake mixes, chocolate to be more specific. And so the purpose of my project was to minimize the moisture loss of baked cakes. And I mentioned baked because obviously I could reduce the moisture loss to 0 by just eating the batter, but I'm interested in a baked cake that is moist. And so that's the purpose. And here's my project charter. I'd worked on this last year with both Jerry Fish and Scott Allen, so they're both mentioned in here. So that's the purpose and background of this project, but let's jump into it. Let's take a look here under the measure phase where we have some data. In fact, I've got a couple of jump data tables. I'm going to open up this historical process data first. And this was actually historical data that I'd gathered on some of the cakes that I'd baked before I even started this project, okay? So you can see this is a little old, but that's okay. I've got the dates and the moisture loss for each of those baked cakes. And so you might be asking yourself, well, how did you measure the moisture loss? Great question. I have that documented here in this JPEG titled Measurement Process. So I'm going to pop that open so you can see what the steps are. So first I mix all of the ingredients in a bowl, then I pour the batter into a pan. And then once the batter is inside the baking pan, I weigh it and I obtained the initial sample weight that I used within this formula here to calculate the percentage of moisture loss. Then the cake is baked. And then after the cake is finished baking, I obtained the weight again in the pan and use that as the final sample weight that goes into this calculation right here. All right, so that's the process I followed to calculate the moisture loss. And here what I did is I saved a script for a distribution. I was just taking a look to make sure my data follows a normal distribution, which it does in this normal quantile plot. That looks pretty good. I also added some annotations here on the right in the text. So that's a nice way to add a little extra information, context, my reasoning for why I did things. So if I have to come back to this project later, I know why something was done. I don't have to guess or go through all the steps again. And to add an annotation, you can use the Tools menu and this Annotate option. And then you can just click anywhere in any jump report and just add your notes if you like. So that's what I did. And in Jump 18, actually, if I don't want to see all of this information, maybe it's a little overwhelming, I can actually just right-click and choose Minimized. So then I just see this little information icon and I can hover over it. And I can just right-click and choose Minimized if I want to display that again. Okay, so here, in addition to visualizing the distribution on this quantile plot, I also went ahead and fit a normal distribution. I have my parameter estimates here. And then I ran a goodness of fit test. Okay, so my Anderson-Darling p-value for the normality test is pretty high, higher than 0.05. So I'm going to say this data follows a normal distribution, which makes it okay for me to use the regular calculation for PPK. Here's the calculation I did. I could have asked Jump to do this. And really, I calculated PPU, right? Because I'm only going to have an upper spec limit. And what I did here is I actually set my new upper specification limit to be the lowest value that I'd achieved previously with these cakes. In fact, let me go back to this data table and I'm going to make this moisture loss column into a label so that you can see when I hover over this point, the lowest achieved moisture loss previously was 3.83. And so I used that as my spec limit when I calculated my PPK, which is negative in this case. So that makes sense because my spec limit, upper spec limit, is below all of my data. So this is a pretty bad process that I need to go ahead and improve. And so going back to this measurement process, some of you might have noticed that I really didn't trust my measurement system. And so I documented here what I did. To ensure the accuracy of the measurements, I took each measurement twice and then used the average of the initial and final sample weights for the calculation. So that's maybe not the best option. Probably I could have done something else, right, Scott?
Yeah, I was just going to jump in here, Marilyn, and I think when you're doing your baking in the kitchen, you might not have, need the tight controls on the measurement system. But did you ever think about doing a analysis on the measurement system for your scale and the whole process of weighing it?
I probably should have done that, right? It would have been easy in here. And an MSA is really a special purpose DOE. So in JMP, the option to set up your measurement system study is under DOE special purpose, right? So I could have created that here and ensured that I trusted my measurement systems. You're right. And easy peasy for the analysis, right? I have it right
Right.
here,
Yeah. And it would have been a simple design. You're probably the only one baking the cakes, so you would have only had one
right?
operator.
Right, exactly. Just one operator. But I didn't do it. I went with the quick and dirty, and I know that a lot of people do this right here.
Yeah.
And so that's what I did. Maybe not the best next time with the
Next.
MSA. Right. All right, so let's take a look under measure. We also have a fishbone diagram. So here I was kind of brainstorming what could be impacting the moisture after baking the cakes. And there's going to be like 4 general categories. We're going to have some factors that we can control, some factors we're going to hold constant, some things we can't control, and some nuisance factors. And for each of these categories under child that I have highlighted here, there are other sub-causes, right? So controllable design factors, for example, I can control the baking temperature and the time for the baking and the cake mix brand that I use. So with the data set up in this way, we can use the Analyze menu, Quality and Process, and the option is called Diagram. We can generate a cause and effect diagram or Ishikawa diagram just by plugging in our columns, and there it is. Now I'm going to close this and go back to the script that I already have because I added more annotations. And I also made some edits to make this Ishikawa diagram a little more, it just changed the aesthetics to make it look how I wanted. So by right-clicking, we have an option for font, and that's where I changed this to bold, or we can right-click just to change the colors if we like. There's lots of options by right-clicking on the cause and effect diagram. So here you can see that my categories are broken down into controllable design factors, the brand, the baking temperature, and the baking time. Held constant factors are going to be the pan that I used, the oven, and the scale, mainly because I only have one of each of these things. The uncontrollable factors, ambient temperature and moisture, we're not going to be able to control that, but we are going to randomize the order of the data collection to sort of average out any effect of these ambient temperature and moisture. And then we also have a nuisance or blocking factor, and that's going to be the day of the week. So to optimize my process, I'm going to have to bake a lot of cakes, and it's going to be too many cakes to bake in a single day. So I'm going to have to gather the data over more than one day. And to account for any extra variation I might be introducing by collecting the data over multiple days, I'm going to add a block to my design. And so here I have the details of my factor levels and ranges for my controllable design factors. So the two brands are actually two real American brands. I've masked their names here to protect the innocent. The oven temperature and baking time, as you can see in my annotations, are based on the recommendations from these two mixes. And I also set my levels a little bit outside of what the cake mix brands recommended. And that is often recommended for a DOE, right? You have a better chance of detecting a real effect if you kind of widen the ranges for the factors. And so that's what I did here. So let's go ahead and take a look at the analyze phase where I have a table with my design factors. These are the factors we just talked about, the cake mix brand, the oven temperature, and the baking time, all with their low and high ranges. So we're going to use this table to set up a DOE, a classic factorial DOE in JMP. So to do that, I used DOE, classical, and I selected factor screening design. Okay. And so first I'm going to enter my response information, and this is moisture loss. And this is something I want to minimize. So I'm going to tell JMP my objective is to minimize this. And my upper spec limit is 3.83. Remember, that was the lowest achieved moisture loss from my historical data. So that's all I need to do at the top. And here I can add factors. For example, the temperature is a continuous factor, and I can type in the name and the levels. I'm not going to do that. I'm going to remove it, and I'm just going to go ahead and load in the factors from the factor table that we just saw. So here are the factors and the levels. And now we're going to go ahead and click continue. Okay, so here JMP is asking me, do I want to construct a main effect design? And I do not want to do that because I think there might be an interaction between the baking time and the cake mix brand, or the temperature and the time. I want to be able to estimate some interactions. And so to do that, I'm going to choose the default option, which is choose from a list of fractional factorial designs. Click continue. And here's my list of available designs. So the first option, I already know I don't want, a main effects only. So we're going to leave that out. Here on number of runs, this is going to be the number of cakes I'm going to have to bake. So I already know the first design is no good. And so I'm going to have to bake at least 8 cakes. So maybe now you see why I need to have a block. I'm not going to bake 8 cakes in one day, but I could do 4. So here under block size, I can choose how many cakes I want to bake each day. And I think 4 is doable. I can bake a total of 8 cakes, 4 of them each day. That's a full factorial design. And that design is going to let me estimate all of the main effects plus the 2-factor interactions. This is the design I want. So I'm going to click continue. Great. As I mentioned before, we're going to randomize. And now I'm also going to go ahead and add some center points to this design. I'm going to add 4 center points, and that's to help me detect potential curvature in the response surface. If I'm just using a high and a low, I can draw a straight line between the average of my moisture loss measurements at the low oven temperature and at the high one. But there might be, the middle point might be a little bit higher or lower, right? So if I add center points, I could detect potential curvature. There are other types of designs as well where I wouldn't have to necessarily add the center points. I don't know if Scott was going to give us a tip here.
I was watching you build this design, and I think I don't think you can argue that this is going to be a great design. But did you consider a custom DOE where you might not need to do all these specifications. You could specify the model that you wanted to build, because if you're putting in center points, maybe you want to test for curvature. So instead of building in the center points, you could specify, the quadratic terms and then the interactions that you think might be there, and then ask JMP to build you the most efficient way to cover that space.
I wish I knew about custom designs when I did this because, like you said, it makes it so easy. I can just tell JMP what I want to estimate, but I didn't know about custom designs at that time. And so I really had to think about what terms I wanted to include and what kind of model I wanted to build. And so that's what I'm doing here. But great tip for anyone that just wants to tell JMP what we want in the end, right?
And you can always build both and then see the similarities and compare those if you wanted to.
Exactly. I meant minimize. I want to minimize the loss of moisture. So yes, I didn't do that in my final design, thankfully, but yes, this is what I did. All right, so let me go ahead and click Make Table so that we can see the results. So what we have here are our controllable design factors. Each row is a cake that I'm going to bake. You can see that we've got a block column. We're going to collect the data for these first 6 rows on the first day, and the second day, these second 6 rows. And then JMP also includes this pattern column, which is pretty cool. So plus, plus, minus means the first factor is at the high setting, the second factor at its high setting, and the third one at its low setting, high, high, and low. And then any rows that have a 0 represent rows with a center point. So for example, we see the oven temperatures at 365 and the baking time at 42 for the center point run. And of course, there's no middle between brand A and brand B, but JMP handled that for me. You can see there's 2 center point runs with cake mix A and 2 center point runs with cake mix B. Okay, so that's how I set up the design. Let's take a look at the results in this other data table, cake DOE. So this is very similar to the table that we just saw, but I've already collected here the response information on the moisture loss for each of these cakes. And the other thing that I did here is I added a column for the center point. So this just tells JMP which rows are corner points in the design and which ones are center points where the factors are at their middle levels. And we're going to add this column to our analysis just to get a test in the output for the center point. So to do that, I'm just going to hit the model button here. JMP already knows what terms I wanted to estimate, including the block or the day. And I'm also going to add the center point column here. And when I hit run, JMP is going to let us know which factors are most important, starting with the most important, which is the baking time, and which ones are least important. We can use the p-values here to decide what we want to keep. I'm using an alpha of 0.05, and I'm going to say this interaction is not significant. So I can just click remove to throw that out, and JMP updates the model for me. And I love doing that in JMP. It's just so satisfying because I don't have to go back to a separate window to take out the terms that I don't want. Everything happens right here and my model is updated. I also see that the test for curvature, that center point, is not significant. We have a high p-value, so we'll go ahead and remove that as well. So I can continue like that and remove all of the terms that are not significant. And it looks like I have my final model here, only important terms. And if we go to the bottom, of course, we have our profiler. So I can see the impact of each of these factors, the direction and magnitude of the impact each of these factors have on my moisture loss. I also have the spec limit showing here since I included that in my design, and I can shift things around to find settings for my controllable factors that will achieve the moisture loss that I want, or I can ask JMP to go ahead and maximize the desirability and find the best settings for me. And that's what I've done here. Now, to keep talking about this, we're going to jump ahead to my saved optimal design here. And I've already saved the same settings that we just saw: cake mix brand A, oven temperature at 350, and baking time at 38. And you know I love my annotations, so I made a note here. The upper bound confidence interval for moisture loss is below my upper spec limit for both brands. So even though brand A has lower moisture loss, if I use brand B, even the upper bound confidence limit here is below my upper spec. So either brand, I could use either brand and achieve my moisture loss objectives. And so I'm probably going to do that, right? I'm not going to leave the brand of cake mix fixed. I'm probably going to use A most of the time, but I like to save some money. So if B is on sale, I'll probably use B. And the same thing with my oven temperature. Even if I set it at 350, it's probably going to vary up and down a little bit. And so to take these things into account, I'm going to use a Monte Carlo simulation, which is available from the Profiler Red Triangle by turning on the simulator. And so now we can ask JMP to simulate for us what the moisture loss is going to be if I bake lots of cakes over time and I take into account the variation in my inputs. So here I'm going to tell JMP the cake mix is not fixed, that's random. And I'm probably going to use brand A most of the time because it has lower moisture loss, but I'll probably still use B maybe 25% of the time. Okay. And same thing for the oven temperature. This is not fixed, this is random. And even if I set my oven temperature at, say, 350, yeah, we set it at 350, it's not going to stay there. There's going to be variation. So we'll say that's 6. And the baking time, I'm going to leave as fixed because that's easy enough to set a timer and take the cake out of the oven when the timer goes off. And so when I click the simulate button, JMP is going to simulate by default 10,000 cakes using these settings and taking into account that variation. So if I click here, I see a little histogram on its side, and we can see there's a little bit of a tail here that's above the upper spec limit. And JMP even calculates a defect rate for me here. And this is great because now I can ask some questions of my process, right? What if I set this process, the temperature at 355, but I can reduce the variation maybe to just 3? What happens to my process? And if I click simulate, we're updating that defect rate, right? So we could meet with experts in the process and think about what changes we might be able to make, hit simulate again, and that's free, right? We don't have to actually make changes in the process to see what the impact might be based on this model. All right, I'm going to show you quickly some results that I have because within JMP, we can actually ask JMP to simulate to a table, for example, 100 rows to a table. And so instead of just seeing that little histogram on its side, we have the variation in the cake mix brand, the oven temperature, fixed baking time, and then here we can see some simulated 100 simulated moisture loss measurements for these cakes. And then we could use that to run a capability study. Now, I did that using a JMP add-in that is available from the new JMP Marketplace. This is the Capability Explorer. And I'll show you those results within my project. And for those of you that are interested, we'll do a demonstration of that. But here are the results. This allows me to evaluate the stability of my process on a control chart. I can calculate my capability indices. I can evaluate the normality of my data. And it's all just within this one report using this great add-in that Scott coded for us.